Thanks, Jeff. It's great to be here. Welcome to the CalCCA 2024 Annual Conference. I am really happy to be here. I want to talk to you about the role of innovation and CCAs in creating a sustainable energy future. I am passionate about innovation. I believe innovation has the potential to change the world. Whether we're innovating small and local solutions or large and global solutions, we're solving problems and we're bringing benefits to people. I have an optimistic belief in the power of innovation to change the world. Our goal is to overcome those barriers and solve hard problems. In many cases, as all of you know, at the beginning, people tell you it's impossible and you're wasting your time. And then when you succeed, you have the sweet pleasure of that same person saying, oh, it was easy, it was obvious. You didn't have to do anything at all. But effecting this kind of change requires innovation, and that's what I'd like to talk to you about this afternoon. I work at SLAC National Accelerator Laboratory, one of the U.S. Department of Energy national labs, located just a few miles north of here in Menlo Park. SLAC's mission is to explore how the universe works and apply that understanding to solutions. We have programs in physics, chemistry, materials, and biology, in applied areas like the electric grid, batteries, and catalysts for things like hydrogen production and solar fuels manufacturing, semiconductors, microelectronics, quantum computers and quantum sensors, artificial intelligence, and machine learning. We're also part of and managed by Stanford University. For those of you who aren't familiar with the U.S. Department of Energy, it's an immense organization. One of the things they do is to manage 17 national labs, SLAC here in the Bay Area, Livermore and Berkeley, and others that you've heard of around the country, like Argonne, Oak Ridge, and many others. Their research spans national security, science and technology, energy and sustainability, environmental management, and even things like human health, biology, and developing solutions to help drive domestic industry. If you stop to think about innovation for a moment, there's not a single kind of innovation. There are a diversity of kinds of innovation. Here's one way I think about the variety of ways to innovate. There can be technology-enabled innovation, where a new invention is the enabler. So, for example, you might imagine that high energy density, long-lived batteries helped to enable the revolution in electric vehicles that's allowing us to electrify personal transportation. Sometimes there's a convergence of solutions. For example, you might think of the Internet of Things being enabled by wireless sensors, ad hoc networking, and the internet. Sometimes a systems approach enables us to find solutions. For example, when we think of demand response, we might think of the system of energy generation, energy loads, and even a systems of systems approach that brings together electrical systems with the water and transportation systems. Sometimes adjacent technologies can be helpful in unexpected areas. We're seeing this all the time now in artificial intelligence, large language models and foundation models, big data, and machine learning. Of course, for most of us in this room, we're inspired by the problem, by the opportunity to bring sustainability and energy equity to everyone in the US and the world. Problem-inspired innovation, and so on. CCAs have a history of innovating and problem-solving for sustainability and social benefit. Innovation is no new subject to all of you. It's an integral part of what you've been doing for years and are continuing to do. A couple decades ago, CCAs were born in response to a crisis, the California energy crisis, the crisis of consumers demanding access to 100% renewable energy, and opportunity, brought by regulatory policy, by legislation, by new business models that allowed CCAs to provide the services that we now all enjoy. CCAs for years have accomplished great things and are continuing to do extraordinary things. To take just a few current examples, among you here is a multi-county effort to build a new geothermal power zone. Another effort that's a regional transition to zero-emissions goods movement, solving the difficult problem of heavy-duty transportation and the last-mile delivery problem. And a new battery hybrid project to reduce greenhouse gas emissions and water use, combining energy storage, energy, and reduced water. What will be the next hard problem that CCAs can solve for society? But the problems are hard, aren't they? The constraints are many. Economic constraints means we need affordable solutions. The infrastructure, particularly the grid, is often already under strain in the same areas where we intend to add even more loads to the grid. We're trying to achieve sustainability, and while that goal inspires us, it also constrains the appropriate solutions. We're generally looking for solutions of scale. Even if we're starting small, we hope that success will breed larger scale solutions. Regulatory policy can be our friend, but it can also be our barrier when it doesn't keep up with our new and most innovative ideas. Often the consumers themselves need to be educated because, as we all know, an educated consumer is our best friend. And most important, we're trying to achieve greater energy equity and environmental justice in everything we do. And there are major challenges in doing that. I want to share with you 3 examples of different kinds of innovation that are affecting or will affect CCAs as we move to a more sustainable energy transition. I want to talk about creating a sustainable and resilient power grid through new battery technologies. I want to talk about decarbonizing industry by electrifying industrial heat and ending energy equity forever by delivering abundant, affordable, and clean energy to everyone. First, batteries for the grid. I think of this primarily as an example of technology-enabled innovation. Batteries, of course, by providing energy storage on the grid, bring many advantages. They allow us to spread the energy generated by intermittent sources like wind and solar across 24/7. They give us a means of managing peak loads so that our grid has the capacity to average out that demand across a 24-hour period. But the scale of the problem of putting batteries on the grid is immense. This is a gigaton scale manufacturing problem to put energy storage on the grid. There are very few gigaton scale industries in the world today. Cement, steel, petrochemicals, not many others. And so if we want enough energy storage to stabilize the grid, we need to find solutions that work on that scale. And several of us are developing batteries that use earth-abundant materials and water-based electrolytes. Earth-abundant materials like iron, zinc, and manganese, so that we can generate the amount of materials that we need without harming the earth or the people who are doing the mining and extraction. And water-based electrolytes that are incapable of burning, so as to have batteries that are safer even when deployed at scale under a variety of stressful and extreme conditions. But of course, it's not that easy. Reliable, high-energy density batteries requires solving a number of problems in materials and chemistry. As the elements move between the electrodes, undergoing oxidation reduction reactions, a lot of things can go wrong. You can have corrosion where you don't want corrosion. You can have side reactions. But fortunately, we're living in a golden age of materials and chemistry, where scientists and engineers have an unprecedented ability to engineer materials and chemical reactions to solve desired problems. And I am optimistic that new scalable battery technologies designed for grid applications will be available within the next 10 years, perhaps by following approaches like I'm describing here with earth-abundant elements and aqueous water-based electrolytes. Now let's talk about another kind of innovation, convergence and a systems approach for decarbonizing industrial heat. Decarbonizing the electric grid, which we've made great progress toward, and electrifying personal transportation are actually among the easier problems in sustainability. But what about the hard-to-decarbonize sectors, like industry, like steel making, cement making, and chemical manufacturing, like heavy-duty and long-haul transportation? So let's take a look at decarbonizing industry. Manufacturing processes like steel and cement are major greenhouse gas emitters, as you all know. And much of those greenhouse gases come from industrial heat, a set of processes ranging from relatively low temperatures like 100 degrees C to high temperatures like 1400 degrees C. And the immense scale of these processes means that they're satisfied largely with fossil fuels, using reactor designs that have been in place for 50, 100 years or more. If we could electrify the industrial heat and using clean electricity move from fossil fuels to electric heating, then we would remove a major portion of the greenhouse gases emitted by things like steel making and cement making. And of course, there are many technologies for creating heat with electricity. There's resistive heating, there's microwave and RF heating, there are optical techniques. And in many cases, these techniques offer precision and control and other advantages in reactor design that the existing fossil fuel techniques don't offer. On the other hand, these fossil fuel-driven reactors have been proven over many decades, and there's a huge installed base and a legacy comfort with how those technologies work. So the transition will be challenging. These processes also require 24/7 energy. And the people we're trying to convince to switch know that sometimes the grid isn't 24/7 reliable, particularly for uses demanding as much power as these industrial applications. I think this is an opportunity for CCAs. I suspect already you're all thinking of innovative solutions to the problem. Perhaps the cement and steel makers should be helped to develop on-site energy storage that might be batteries or hydrogen generation or even thermal storage. And perhaps CCAs could help them to do that. Or perhaps the CCAs want to own that energy storage outside of the fence line of the industrial customer. Perhaps there can be a systems approach that combines these industrial uses with other large uses in a sort of demand response scenario that allows you to meet the needs of these applications while minimizing or managing the additional load on the grid. So this is both a challenge and a business opportunity for CCAs. Finally, I want to talk about energy inequity forever as an example where adjacent technologies and problem-inspired innovation can take root. Our goal, all of our shared goal, is to achieve pervasive and persistent energy equity. When I think of energy equity, I think of a couple of things primarily. Providing abundant, affordable, clean energy to everyone so that everyone can have air conditioning if they need it to deal with the effects of climate change, so that everyone has the ability to charge an EV at their home. And secondly, I think of making sure that people can live free from the pollution that can come from polluting power plants and industry. We all know how hard these problems are to solve, how established the historic roots of these problems are. We're struggling with a grid that may not have the capacity to provide the energy to these communities. Serious economic challenges, and perhaps others. But we, collectively, CCAs, are in a good position to fight this problem. We can try to create new business models that allow us to deal with the large upfront capital cost of establishing solutions so that people can then reap the benefits of better economies going forward. There might be value in segmenting the population and dealing initially with the most vulnerable population, people, for example, who can't easily leave their homes when there's a power failure during a time of a stressful environmental problem or some kind of natural problem like fire or something else. Again, this is a great opportunity for CCAs. We all want to address the problem of energy equity as a matter of humanity and integrity, and no group of organizations are better situated to do that than CCAs. So where do we go from here? The problems are many, but our innovative powers are also great. We need to try to knock down barriers. We need to find faster ways to innovate. We need to seek new solutions and new partnerships to get there. Thank you very much. I believe we have time for questions, and I believe you all have the ability to enter questions on your phones. People can come visit SLAC and the other national labs, and it's great fun. The engineer, the adult or child engineer in all of us can really enjoy seeing science and engineering and technology at scale. I believe all the national labs have public programs. They all care about good relationships with the communities where they sit, and so I'd direct you to the National Labs websites. You can usually find your way to community engagement and tours. You can also invite people from the National Labs to come to your meetings. But more than that, the National Labs and the Department of Energy can be a terrific partner for many of the things you do, because they bring a group of scientists and engineers, resources and experience that can be helpful to you in a variety of ways. For example, to pick an example I'm familiar with, the Grid Research Organization where I work develops commercial-grade software solutions in the grid space, and many of our utility partners are able to deploy our software on live customers as ways of testing things like new ways to manage EV fleets, new ways to use storage, new business models like transactive energy, and so on. So we have some questions coming in now. We have a couple of questions asking, what are some of the important innovations coming on the energy horizon and the most promising new energy technologies being developed at SLAC and elsewhere? I've already mentioned batteries for energy storage. I am tremendously excited about the potential of batteries. The batteries that we have are already good enough for personal transportation. Efforts are directed towards getting them even better, where they can start to make an impact on heavy-duty transportation. Of course, we're starting to see the rollout of batteries on the electric grid now, but as I mentioned, within the decade, I think we're going to see even better batteries that are purpose-designed and built for the grid. I'm also tremendously excited about what's going on in the chemistry and catalysis space. I think we're going to develop new technologies to produce hydrogen efficiently, to produce solar fuels, chemical fuels for all the advantages that chemical fuels bring without having to pump oil and gas out of the ground to make them. The energy density of chemical fuels, of course, is extraordinary. It's what allows you to fill up the tank of your gasoline car and drive to San Diego without stopping to fill up your tank again. So there'll continue to be a place for chemical fuels, and if we can come up with carbon neutral chemical fuels, that will be a huge advantage. New grid technologies are going to continue to help us. Just in the last few weeks, you've read in the popular press about new conductors, new cables, that can increase the capacity of the grid without having to build new, from scratch, long-haul transmission lines. Although I didn't mention it earlier, when we think about industrial processes like cement, steel, and chemical manufacturing, the switch to electrical heating is going to enable new reactor designs that might bring new precision, new control, new quality to century-old manufacturing technologies. And our ability to do things like upscale plastics, so that in recycling plastics to keep them out of landfills, we're not merely grinding things up and producing lower grade plastics, but we're going back to the starting components of plastics, so the recycling process allows us to make new plastics as high quality as the initial ones. We have a number of additional questions on energy storage technologies. As many of you know, the world of long-duration energy storage is currently a world of incredible variety, although I've focused on electrochemical energy storage in the form of batteries and chemical energy storage in the form of using excess electricity to produce hydrogen that could later be burned directly or run in a fuel cell. The universe of energy storage technologies is greater than that. And there are gravity-based technologies that could either take advantage of pumped hydro or massive objects. There are thermal energy storage that could either be used to convert back and forth between thermal and electrical, or in the case of industrial heat, perhaps the thermal can be used directly. So we're at a moment in time where people are exploring a remarkably wide range of long-duration, stationary energy storage technologies. And I believe during the next few years, we'll get a better sense of which are the winners, which are the losers, and in which particular areas and applications each one fits the best. We also have some questions coming in about artificial intelligence and machine learning. We've all been wowed by the ability of things like large language models and foundation models to do amazing things in answering open-ended questions, in taking diverse and heterogeneous data and applying it in eerie ways to specific problems. And so everywhere I go at work with my partners and collaborators and with all of you this afternoon, people are exploring how can we use technologies like large language models. Again, I think we're in a moment of exploration there as people try to understand the usefulness but also the risks and limitations of those technologies. Clearly, they bring a lot to bear, particularly in helping us to apply diverse information to whatever specific problem. But clearly, things like pervasive bias and hallucination worry us about those very same technologies. So this is very much where the state of the art of research in those technologies is today. Understanding how to train those models, how to use those models, and where we can trust them. Among the approaches I'm most excited about is using physics and other guidelines as guardrails to limit the range of options that these technologies share with us, with the hope being that by constraining the range of possible solutions, and maybe by testing those solutions, we can increasingly use these systems in mission-critical applications, not just helping us with a first draft or a revision of some paper that we're writing, but with things like autonomous vehicles, or running power plants, or running chemical plants, or doing commercial air traffic control. These are mission-critical applications where mistakes lead to people dying and billions of dollars of damage occurring. So these are cases where our tolerance for mistakes and errors is zero. But active research is helping us discover ways to use these powerful techniques even in mission-critical applications. And I believe in the next few years, we'll start to see what the power of that is and develop confidence in that. We continue to have a lot of questions about batteries and EVs. Let me try to pick a few out of here. A couple of the questions have to do with battery recycling and battery waste. We're right to be concerned about this. We don't want to fill our landfills. There's a number of encouraging signs. One of the best and most successful examples of recycling in the modern world is the lead-acid batteries that have been the 12-volt power source in internal combustion engine vehicles for decades. Virtually 100% of lead-acid batteries get recycled. It's a remarkable thing that we all take for granted. So it can be done. In the case of lithium-ion batteries, we're seeing the recyclers and the recycling technology growing up side by side with the development of manufacturing. If anything, the recyclers in the lithium-ion battery space are waiting for lithium-ion batteries to be available for them to recycle. So that gives us some hope that there'll be a vibrant recycling industry for lithium-ion batteries and other advanced batteries that are developed going forward. It will, of course, be many years before recycling solves the problem that I talked about earlier of having to pull massive amounts of elements out of the earth. Because if you pause to think for a moment, at any point in time, you're manufacturing batteries based on today's demand, and you're recycling the batteries that are at their end of life, the batteries that you deployed, let's say, 10 years ago. So when a field is growing rapidly, as lithium-ion batteries for personal transportation are today, the recycling industry will only generate a small fraction of what's required for many years to come. Thank you all very much for your attention and questions. I look forward to talking to many of you this afternoon.